Okay, so hi Ani.
Hi Janakiraman. Yeah, thank you.
So I was wondering, why don't you throw some challenges at me this time?
Absolutely.
Okay.
Absolutely. So maybe let's start with some simple circuit like we did last time.
Okay.
So shall we start with a couple of series parallel questions?
Okay.
Okay, maybe take the first one.
Okay.
Let us say starting from the left to right.
Yeah.
I am going to add a series resistance.
Okay.
And then
shunt R1.
R1, a shunt resistance R2.
Okay. Okay.
Then I am going to add a series resistance again.
Okay.
Okay, from the top.
Yeah.
I'll call that R1.
Okay, again it's
yes,
R1.
Again another one.
Okay.
And then another shunt resistance R2.
R2, right?
Correct.
Okay, great.
Yes.
So effectively I have 1 and 2 here. This is also R2.
That's right.
Right? And what we are now trying to do is to find the equivalent resistance.
That's right. That's right.
Okay, so I'll follow your footsteps. Okay, and I can see that this seems to be something that can be simplified simply because the current entering R1 has to flow through R2 as well, and therefore the two resistances are in series. Right? So therefore we can redraw this as R1, and then there is an R2 with in another equivalent resistance of R1 plus R2. Okay.
Perfect.
And right. So now we go one more step further. I can see that this again is sort of between the same points whose potentials are the same.
Right.
And therefore the resistances have to be in parallel. Right, and therefore if I look at the R equivalent here, I can just write it as R equivalent equals R1 plus, I'll again go back to your notation, parallel R1 plus R2.
Perfect.
Okay, so this is what we have, and if we put, for example, R1 equal to R2 equal to R, then what we get R equivalent as R plus this is 2R, and so R into 2R divided by 3R, right? So what do we get? We get,
so it's R plus 2R by 3?
R plus 2R by 3, 8R by 3, right?
Yes.
8R.
Oh sorry, 5R by 3.
5R by 3, yes. 5R by 3.
Perfect.
Okay, so this was nice, but let's say I want to make this slightly more interesting. I add another branch of this R1, R2, one series, R1 series, R2 shunt.
Perfect.
I add one more. I add another one like this.
Maybe
so,
if we do add one more section, we may see a pattern.
Okay.
Right? Shall we try that?
Yeah. So we can do that. So we go down here. Okay.
So now you're going to add a series shunt, series shunt, and then another series shunt.
Yeah. So I am going to say R1, R2, R1, R2, and another one.
Yes.
Right? R1. Okay, I am going to use this new notation now because I don't have to short all these points, right? So I am going to call this as node 1 and this as node 0.
Perfect.
So I am calling this the ground.
Some kind of reference node.
Some reference node. So I am going to use this notation going forward. So this is R2. So there is, any shunt resistance that you spoke about goes between that node and ground. Okay. So effectively this is like having one long wire like this. That's all. And I can call this node 0 if you want. Okay.
Perfect.
So yeah. So if you, how would you solve this now?
Okay. So I already, of course, we could follow from brute force. Right? I know I see R1 and R2 in parallel, then in parallel in series, then in parallel with R2, and then I can do a bunch of combinations.
Yes.
But I suspect that there must be an easier way. Right? Because we have solved the previous question.
Correct.
Is it possible? See, because we said we are adding one more section.
Yes.
So the previous one is already hidden somewhere in here.
Correct.
Maybe we can use that
to
figure out what will happen by replacing that one with its equivalent resistance.
Correct. And if I were to make this more interesting,
oh yes,
I want to go on doing this
forever.
R2 forever, right? So I have added one branch, 2, 3, 4, and I am just simply going to do this
That's interesting.
infinite number of times.
Oh wow.
Right?
Okay.
So the moment you go to infinity, you don't know, you can't solve it. So what we are doing is we are going to the last node, solving the series, then bringing it to parallel, series, parallel, and we keep coming forward, right? But now that infinite node is not, you know,
Available
not
to
there,
us.
right? It's not available
So
to us,
we need
right?
to figure out some other way.
So what do we do then? How do you think we can solve such a problem?
Okay. So obviously we can't do it from the other side.
Yeah.
Maybe we can start from the left side and try to do something.
Okay.
Right? Well, unfortunately what is happening is, so you have now drawn the infinite network.
Yes.
Right? Let's see, I have R1, R2. So I see a repeating pattern.
Yeah.
And it's going all the way to infinity.
Yes.
Right? So maybe I remove just one section out.
Yeah.
And maybe replace everything else with something.
Okay. Right. So now you're saying this, right? R1, R2 down to ground.
So in fact, let us just maybe draw a box.
Yeah.
Right. So we don't know what is there inside that, right?
So this is some box.
Okay.
Okay. Whose equivalent resistance is R equivalent and between that node and ground.
Yes.
Okay. So the interesting question is there any relationship between this equivalent resistance and the equivalent resistance as seen here?
Okay. See, if you really have an infinite network, then it looks like it doesn't matter whether you remove one section or add one section.
Exactly.
Right?
Right. So therefore, in some sense you are saying that the equivalent resistance, let me call this 1 and 2 actually, R equivalent 1 should be equal to R equivalent 2.
That
right?
makes sense.
Yeah. So if you look at this point and just look at that infinite,
I again have an infinite number
you
of
have an infinite number of them, right? Therefore, it doesn't matter if you're looking from 1 or from 2 or from 3 actually, right? So you can as well do this from any point. So we might rather do it from the easiest point, which is 2.
Yeah.
Right? So what you can do is construct R1, R2, and the equivalent resistance I will replace, I'll just call that R.
Oh, okay. This is very simple. Okay.
Okay. And I'm going to say the resistance as seen from here is also R because it's essentially an infinite ladder as we discussed, right? So now this is something we know how to solve,
yes.
right? As you mentioned, you again come back here, you see this combination,
yes,
they are between same potential Vx and ground, and therefore they are in parallel, and therefore the equivalent resistance R, okay, can be written as, okay, before I get into that, can you give me an estimate for the range of R?
Okay. So it of course has to be larger than R1.
Yes.
Because I have something in series with R1.
Yes.
Right?
Yes. So therefore I'll do this greater than R1.
Yes. This much I can tell.
Yeah.
I'm not able to pick out some other pattern because the other portion which is coming in series with R1 is smaller than R2 is smaller than R. Right? Because you have those two in parallel.
Exactly. So R therefore has to be less than or equal to R1 plus R2.
Yes.
This much we can say?
Yes.
Surely?
Correct.
Right?
In fact, or R1 plus R as well.
R1 plus R as well, right?
But I'm not sure whether that will give you anything useful.
Useful, right? So it just says R1 is greater than 0.
Yes.
So yeah. So at least we know some estimate of where the resistance, equivalent resistance should lie.
So it lies between R1 and R1 plus R2.
R2, right? That much we can easily say. Okay. So therefore, let's go ahead and solve this problem.
Actually, I understand why. Can you go back to that? I think I understand why. I just got some idea. So if R were 0, then R2 would get shunted by a short circuit. That would give me this case of R1. And if R were open circuited, infinity, I would get R1 plus R2.
R2.
Right? Those are the two extreme cases.
Extreme cases.
Perfect.
Exactly.
I think I understand.
So therefore, it's a good estimate to keep in mind.
Yes.
Right? So R1, R2 and R, okay, and this is also equal to R. So we are saying the equivalent resistance, so this is also R by the way, okay, is R1 plus R2 in parallel with R.
Yes.
So let's go ahead and solve this completely. You get R2 into R by R2 plus R. Okay, and I can simplify this. I'll just take R2 plus R, multiply on both sides, right? You get R into R2 plus R equals R1 into R2 plus R plus R2 into R.
Yes.
Right? So I can simplify this. R2 into R plus R square equals R1 R2 plus R1 into R plus R2 into R, right? These two are off, and therefore I can say R squared minus R1, R1 into R plus
minus
R1 R2 equals 0. So
I'm
this
getting a
is
quadratic equation.
Exactly. So this is of the form ax squared plus bx plus c equal to 0. Okay, and we know that the solution to this is minus b plus or minus p squared minus 4ac by 2a.
Perfect.
Right. So let's just go ahead and substitute this. For us, a is 1, b is minus r1, c is minus r1 r2.
Yes.
Okay. So I'll just put that equation here again, minus R1 R minus R1 R2 equal to 0, right? Is my equation right? Yes, it is. So I'll say R is equal to minus B, which is R1 plus or minus square root of B squared, that is R1 squared minus 4AC, so that becomes 4 R1 R2 divided by 2.
Okay.
Now we have two solutions.
Yes.
How do we pick?
See, I have R1 plus or minus root of something.
Yeah.
That in the one inside that square root seems to be larger than R1 squared.
Square. Exactly.
So the square root of that will be larger than R1.
R1, exactly, right? So I'll just put what you're saying in writing here, R1 squared plus 4 R1 R2 is actually greater than root of R1 square, which is therefore greater or equal to R1. So if you take the minus sign, you will get R as a negative number,
resistance,
which basically has no meaning here.
Yes.
Right? So therefore it has to be only the positive root.
Okay.
So R will be R1 plus root of R1 squared plus 4 R1 R2 divided by 2.
Okay.
Right?
I see.
So this is what we get, and so let's take the simplest case when R1 equal to R2 equal to R.
Okay.
Okay.
That's what we did for the first example as well.
Exactly. So what did you say? You said that the no, I cannot use R. I will use R naught.
R naught. Okay.
Some common value. Okay. So you said that the equivalent resistance R should be greater than or equal to R naught and less than or equal to 2 R naught.
Yes.
This is what your estimate was.
Correct.
So let's see what we get here. You will get R naught plus root of 5 R naught squared, that is R naught into root 5 by 2.
So R naught into 1 plus root 5 by 2. Okay.
Okay, and I think I worked this out.
Okay.
This is approximately 1.67 R naught.
Makes sense. Root 5 is about 2.2, 2.23, something like that.
Correct.
Okay.
Right. Okay. So you get something like 1.67 R naught. Okay, and which of course is between 1 and 2.
Makes sense.
R naught. Okay. So this is one of the methods that you can employ if you see like an infinite ladder or something like that. But is there any physical application to such problem?
See, most of the circuits may not have an infinite ladder, but you need something really large, right? It doesn't have to be infinity.
Correct.
It needs to be really large. Let me see. See, I heard one civil engineer once told me that, for example, you need to make some electrical measurements on a reinforced concrete to test the quality of the reinforcement. They put in metal inside concrete.
Right.
So I can now imagine a very large wall or a bridge or a building or something. I have access only to 2 terminals.
Wow.
But I now have, like, let us say, a long reinforcement, something like that, maybe. Right.
Okay. So you can at least make out if it's like broken somewhere.
Or something like that.
Okay.
Right.
Okay, that's an interesting application. Yeah, but anyway, as an electrical engineer, we should just enjoy solving various kinds of problems like this.
Absolutely.
The applications we will point out as and when we come across them in different courses. Okay.